having established what a rate is, rate comes as instantaneous reaction rate, right? So whenever we say rate, we mean the instantaneous reaction rate. Let's now talk about rate laws. And with law, I don't mean really the term law as it has been, as you might have seen it in the scientific method. In the scientific method, as it's presented in the textbooks nowadays, you kind of make experiments, you form hypotheses, you do observations in some random order, and then from these observations, you observe a pattern, and if this pattern holds, you can call it a law. That's, for example, the law of conservation of mass. And that's a general pattern that holds across the board. Now, this is not true for kinetics. Laws don't hold across the board. This is rather more, it holds in many cases, it doesn't hold in all cases, so you could call it approximations or mathematical models to describe rates, but it's definitely not a law. It's just that when the term rate laws was established in the early 20th century, at that point the term law was not used in the way the educational department uses it today. So be careful, but probably, I don't know, if there's anybody who is really digging this scientific method thing, don't get upset about this. So what does it mean? The differential rate law, there's three types really, and two are very much related with each other, and they are called differential rate laws. Differential rate law for a net reaction, so this is a differential rate law at the beaker level, and at the beaker level or macroscopic level, that one has an alternate name that is called empirical rate law. So this comes with a bit of a confusion. It's a differential rate law for a net reaction or an empirical rate law. And then there's the same kind of thing that looks mathematically pretty much the same, but it's at the microscopic level, at a molecular level. What happens when I hit molecules, not what happens if I mix solutions. And as opposed to those two, which look mathematically very much the same, there's one that looks mathematically very different, and that's the so-called integrated rate law. And that's really not a good topic for this course. It's mentioned in the textbook, and I will mention it very briefly because you really need calculus to understand this. And unless you have calculus, you have to memorize a bunch of formulas, and I'm not a big fan of memorizing formulas, so I will brush over this pretty much. So what's the difference really, mathematically speaking? In a differential rate law, the rates are related to concentrations. So the rate, there's no time in there anymore, right? So the rate is just related to what is the concentration and what might be the concentration of other chemicals. I could go on depending on how many reactants I have. What counts are the number of reactants really. And then I can express the rate as the reactants raised to some power, and this L is very likely an integer, so a whole number, but it could be a broken number. There's nothing that forces it to be an integer. It's just very likely an integer. And then there's some proportionality constant in front. And that depends, of course, on the reaction. Different reaction, different proportionality constant. And the differential rate laws all look like that. The rate is to some extent proportional to the concentrations raised to some power. And the powers are called orders. The integrated rate laws, on the other hand, take the concentration at a time and relate that to time itself. So this is the initial concentration. It's not time dependent. It's just a constant, right? That's how much I start out with. That's a constant. And then there's a function that depends entirely only on time. It has the same proportionality constant. There's a k in it. But that's an exponential function that depends on time only. So there's no rate even in it. The rate is in this function. The rate is implicitly or tacitly kind of under the table, under the rug, because now I know what the concentration does as a function of time. Of course, this is much more valuable to have, the integrated rate law, than the differential rate law, because I'm not really interested in rate. I'm really interested on what does the concentration do as a function of time. But it's very difficult to get this. So here it is again, and this is all I'm going to say about integrated rate laws. The equation for this curve, right? So I told you, when we take measurements, we kind of look at the reaction in time, and we measure how does the concentration of a reactant go down, or how does the concentration of a product go up. And of course we don't get a smooth curve. We get some points, and the points will be noisy, or there will be a product going up, and again we get some points, and the points will be noisy. And in the most simple instances, we can get this curve by fitting it to a simple mathematical expression, but that's only in the most simple instances. If we know something and create just the right conditions, this can be done. But this is extremely rare. In general, this is not possible. You can't just fit a curve to this and hope to get the right integrated rate law. This is not a general method. But the integrated rate law is really, really hard to get. And I'll explain on the next slide why that is. So this is an example, and this is a common example. This is, for those of you who have seen this is similar to radioactive decay, and that happens in kinetics too under certain circumstances, that the concentration at a time t depends on the initial concentration of a reactant, and then there's simply an exponential decay going on. And that's how I created this graph, right? And under certain circumstances, this can be true in chemistry too. And if this is true, of course, then you can simply fit your experimental data to an exponential decay and get this curve from the data directly. But this is not generally true. So what is generally true? So here's the rate law way of the world, so to speak. The first step in this game is to collect experimental data. So you do the experiment, and what is collected are for as many chemicals as you can, what is the time change in the concentration. And that's not only reactants and products, that will be other chemicals as well, because there will be something, when we look at mechanisms, right, there will be something like intermediates. You remember there was something like a substrate enzyme complex in the Michaelis-Menten mechanism. And if you only know how much substrate or how much product you have, it would be great to have additional data how much substrate enzyme complex you have at any time to be able to say something about the kinetics of this reaction. Then there is a data analysis step, and that leads you to the differential rate law. And the differential rate law can be, as I said, it can be you decide I'm doing that at a beaker level. And at the beaker level, you look only at reactants go to products. So I'm modeling the speed or the rate of reactants go to products. This can work, or it can go awfully wrong, right? The alternative, if this works, great. If this goes wrong, here's the answer what to do, right? We go over that in a second. Once I have this equation, I use calculus, and we can't, which is why I don't do that, to obtain the integrated rate law. So as long as this differential rate law is relatively simple, mathematically speaking simple, I can use calculus, straightforward calculus, and to solve this and get the integrated rate law. That's perfectly possible. And if you're a chemistry major or if you're a physics major, you will do so at the 300 level. In biochemistry, I don't think so. They don't do that. But in physical chemistry, we do that. But that whole thing here, in particular the last step, works for simple reactions only, and for the beaker level in particular. If we deal with a complex reaction, right, and in biochemistry in particular, you deal always with complex reaction, and the same is true if you say you want to model combustion and you have 1,000 different intermediates, or you want to model atmospheric chemistry and you have plenty of different intermediates, then there's lots and lots and lots of different rate laws, and each rate law is called a mechanism. So each mechanism comes with its own differential rate law that is a rate law for a molecular, right? It's a molecular differential rate law. And then the only thing is, we can't do this with calculus anymore. Calculus just doesn't do the trick. You can actually prove with calculus that calculus can't solve it. The only thing that you can do is, and this is now the revolution of computers, that computer simulation can do that. You can do computer simulation, and computer simulation can kind of disprove mechanisms. So it can show, oh, this mechanism can't possibly account for the experimental data, throw it out. This mechanism can't possibly account for the experimental data, throw it out, right? It can never prove a mechanism, but it can disprove mechanism. And that's how you proceed until you have only a few mechanisms left, and then you know what kind of additional experimental data do I need to distinguish which of those are kind of can I disprove.